Hey, what's going on? It's been a little while since I did an update on the chili pepper. We were out 2 weekends ago at Bakersfield testing and ran into a problem. Voltage issue. Anyways, we yanked everything out to inspect, and I don't know that I've ever gone over this since we've been making this kind of power, but I'm going to show you some secrets here that aren't really secrets, but I'm going to actually show what we're doing here and how we're doing 2,000 horsepower with this engine. So chili peppers up in the air here, and of course there's nothing underneath it. There's the dog there. We're running a power glide, reed case, nice setup. EV1 converter, a little tight, but we're turning it up and it seems to be working. So here it is. So we yanked it all apart and just for inspection to see what was going on, if anything was going on, and decided that the piston wall the pistons aren't exactly designed for this kind of power. So they were expanding and almost just barely about to touch the cylinder wall. I'm gonna grab a flashlight here. Right up. Let's see, that's the number 8. Right way up at the top. Yeah, you can see it right here on the number 4. So we had this honed, but right there above the top ring, a little bit of touching. And that is from essentially the piston no longer being cylindrical because of the heat from the cylinder pressure expanding it more on the top than everywhere else. It didn't touch anywhere else. So I'm like, okay, let's take this in. Also decided to check out the Valvetrain, we'll go over that. But anyways, these are Maul pistons, and the piston wall clearance was 1 1/4 thousandths of an inch. You heard that right, it's 1 1/4 thousandths. It took 3 10,000ths of an inch to clean everything up. In other words, this block is straight as an arrow. Now, please note, pay attention here, that this is not a, quote, reinforced block. This is the Ford Performance, right? The original Ford Racing aluminum block. These are the original sleeves. This is not a sleeved motor. These are 10-over pistons. No sleeves, no fire hoops, no nothing. Okay? It's not needed. The way that we actually get this block to handle this kind of power is from the mid plate. We run this mid plate here. No motor plate, just a mid plate. Let me flip it over, check some things out. So this is running a factory crankshaft. It's a Gen 2 crankshaft that has been massaged. It's been knife edged and polished. That's to, knife edging is for windage, not necessary for strength, but it's always nice. But the grinding and the polishing of the casting reduces the stress risers. Where a crack is going to propagate is on the surface, so when you flex these crankshafts, which we are definitely flexing these crankshafts, at this power, when you flex the crankshaft, there's going to come a point when it's going to want to crack, and that crack will actually propagate on the surface on the rough casting, like the rough casting on the caps here. Okay, so if you remove that, even though you're removing material, you actually strengthen the surface and you strengthen the crankshaft. So we've had no issues so far. This crankshaft is straight as an arrow. In fact, the block was straight as an arrow. And then we have our scraper here. Aside from that, these are steel rods. These are the Callies. They're the Timken steel. They're the strongest rod you can get in steel. And then ARP hardware. Honestly, the ARP hardware is not even necessary. But at this level, throw it in, right? So, 2,000 horse flywheel. So 1688 at the tires through the power glide. on drag radials, which eat up a ton on the dyno. So that's what we found here. It was a hone, left the same pistons that we were running. There was no issues with them. I didn't even change out the rings. Checked the gap. Another little tidbit, secret, if you want, the top ring is gapped at 18 thou, the second at 25. They were inspected and have not butted up. We run piston squirters on this to keep the pistons cool. And the tight clearances keep the rings in the piston. You can see that piston to wall clearance is tight, tight, tight. If you can see it, whatever. But the more you keep the ring in the piston rather than out in the open exposed combustion area, the cooler it is. Okay, so found some issues. Ran too fast for the push the nose in and was running quarter mile stuff. Had some bugs there, but the engine, let's go check out the heads. Oh, wait a minute. Valve springs, the Valvetrain was inspected. The pack 1, 2, 3, 4 X's, God, I hate those. They didn't do too well on these. In fact, I've not seen good stuff from them. When they're shimmed like very, very tight, they can last a lot longer, but we don't run them. So this experiment was to run different pack springs, and we ran some on the intake side, the 1213s, and the exhaust side, the 1214s. So these are 1213s are listed for a Coyote. They're actually about 93 pounds seat pressure and 190 open with the 13 millimeter lift cams. So the goal was to actually reduce the harmonics, because it's the harmonics of the Valvetrain that caused the 1, 2, 3, 4 X's to fail. It's not the spring, it's just it's a poor match for a mod motor with the resonant frequency. And so you can run lighter spring pressures, especially on the intake side. The exhaust side was locked out. We had about 120 pound seat, 275 open. And we checked everything. So let me just open up these bags and I'll show you. So the spring themselves, still, when we checked them on the test bench, had lost nothing. This motor has, I don't know, probably between dyno and drag passes, 120, 140. So decent. This retainer, which is specifically for the 1213 X's, actually is where we saw an issue. So they were a little hard to get out, but not really that bad. There's no material transfer between the lock and the retainer here, which is from floating. So we weren't getting float, even with 190 pounds open pressure with the cams we run. But when you turn it over, actually this one looks really good. You see the material is missing from where the spring was sitting, and it matches here. So this was good. Now I believe on some of them, yeah. So I did take this motor to 9,000 RPM on occasion in the burnout and on the dyno. So a couple of them actually showed where the spring was rotating underneath the retainer here. And I said the spring was rotating because we had seats in this, and the seats are here. So here's the spring seat, and it was rotating on the bottom. Actually, this should show some, no, it was on the aluminum, that's right. So we had minor resonant frequency with the very weak springs, no valve float. So these are the 1213 X's. They are listed as a comp part number with a full kit. for the Coyotes, I would see these as a very a nice upgrade, honestly, over Gen 2 stuff. Over on the exhaust side, these are the 1214s. These are used in GT supercars. And again, the spring tested just fine. The retainers showed the same. These ones were locked in pretty hard, but they did have a lot more pressure. So, and again, no material transfer between the lock and the retainer, but every single one of these retainers shows that the spring was moving around. And then these were running a stock valve stem seal. So the seat was stationary and they were rotating around on the seat as well. There's no loss of material here. It's just the hard anodizing or coating that they put on these steel retainers. And the same with the spring seat. But the reason why these will rotate is from resonant frequency. They start to vibrate and then they move around and they turn. So I saw that and said, okay, let's see what we have as an option. There are two options that we came up with after doing further extensive research. Now these springs never floated. I'm not gonna say they floated because they didn't, and they still test fine. So they're not wearing out, they're not having excessive heat buildup from the frequency. And I was pushing them pretty damn hard. I mean, this motor made great power past 8,000 with stock exhaust cam and the intake only cams, which are small. So what we ended up with was two different sets of spring options. Both of them are a different design. So the pack springs are available for these are all beehive. So it's a standard beehive, which is what Ford uses factory stock. It's a beehive. These are the heads here. Oh, and I decided to do a little bit of port work to them. Not on the intake side, but on the exhaust. Anyways, we went with a conical spring. So the Manley Next-Techs are a conical spring. This is the Manley Next-Tech setup. So we have springs that are equivalent to the comp kit or the pack 1213s. These actually will have the same seat pressure, slightly more open pressure, as you see at 226, given 570 lift. So still a little bit more spring pressure and good coil bind. So these are good for actually 600 lift, which is kind of cool. So these are going to be a conical design. So they're shaped like a cone here. Now, because I wanted more pressure on the exhaust, we've had customers running these, by the way, at about 1750 to the tires. Full VCT control with actually these ones. These ones are the stiffer ones. So these ones are supposed to be 118. And the retainers actually move them up on the seat on the installed height because the coil bind's closer. So when these are installed, these will still take 600 lift. And these two are a conical design. So interesting, you can only get titanium retainers for these, and you can only get steel retainers for the other ones. And then these ones take spring seats, so you have to get spring seats. They will work with factory valves, aftermarket valves, triple groove locks, single groove locks, whatever you got. So these are cool for, Manley Next-Techs are cool for 600 lift cams. The next ones that I installed over here are actually also conical and all titanium. This is a half set of the different stiffnesses. Again, we're looking at 90-pound seat on the intake and 120 on the exhaust. These ones come with titanium retainers, spring seats for both, and they're only good. The coil bind is very tight. So 13 millimeter cams, you got to check your valve spring installed height. The intakes are at 155 and we're fine. The exhausts are at 1525 and again are fine but close. And that's the way that these came set up. So the retainers themselves can manipulate where the locks actually seat. So you can see that the locks will sit either in it a little bit or out here and then in here just slightly, if you can see that. So that will determine the installed height. They do manipulate this to get the install heights where they want. These are not good for 600 lift. They have coil bind, both of them at 960. So 960 to 970, they're listed. We tested them. It was about 957 on one, 960 on the other. Anyways, these are going to be cool because they do have even more open pressure on the intake side, about 260. And the exhaust side should be, I believe they were 290. They came in right as tested. Let me check the box here. No, they're not listed on the box. That's wonderful. Anyways, these are running in cars out there. Haven't tested them. Don't have any customers testing them. They're not. I talked to the guy that was in charge of testing these and designing them, and they say that they're done in-house. They're not done by PAC or any other company. So kind of cool. But it's the resonant frequency that we have to change. The conical design in general, and I'm not an expert on valve spring frequency. I know about it. Essentially, it is it's related to RPM and the frequency at which certain metal parts, like springs especially, will vibrate. And when they dance around, you're going to lose connection. You're going to lose. It's actually going to dance between the retainer and the seat, and it'll lose connection there. It'll actually start losing positive seal of the valve, and you can have valve bounce and all kinds of crazy shit. So we reduced it by a good factor when we got rid of the 1, 2, 3, 4X's to remove all issues that we saw on the dyno or at the track. But further along, a conical design should move that frequency to a higher enough RPM that we're not going to hit, which is the goal for a mod motor. It'd be different for other motors. Every motor is going to be different on the frequency at which the springs are going to have an issue. So these aren't like for Harley Davidsons or LS's, shit like that. So these are specific for the mod series. But we're going to test them. And I'm going to throw this thing back together and hopefully get back at it in a week or so out at the track. But that's an update on the chili pepper. Everything else seems to be going all right. Got a bunch of little bugs to work out, but it's a race car. What do you expect? Hey, have a good one, guys.